So thanks, this little chunk just gives you a bit of extra practice at the intermolecular bonding ideas we introduced recently. I'm going to chuck some questions at you and pause the video, have a think about your answer for each one, and then check the model answer I give. They're going to be somewhat thought-provoking. My anticipation is that you might well struggle with each of them, but then as you look at the answer, it'll build the skills that you need. So the first one is, if you're shown a molecule, you could be asked to state all the types of intermolecular bonding that could occur between molecules like that. So have a go. Okay, so hopefully you spotted that with the OH group, you could definitely have hydrogen bonding. It's got the requirement for hydrogen bonding, an H bonded to an atom like NO or F, an O in this case, making the delta plus H, and then on the second molecule you'd have the delta minus O with its lone pair. However, it is the case that you have polar bonds in this molecule, the delta plus carbon, delta minus oxygen, delta plus hydrogen. So anytime that you've got permanent dipoles, you can have permanent dipole, intermolecular bonding. And that's simply, if the molecules don't line up properly to do a hydrogen bond with all the lone pair of electrons exactly lining up with the delta plus hydrogen, you can still have the electrostatic attraction between the opposite charges on the two molecules. And then thirdly, if you're asked for all types of intermolecular bonding, all molecules can do the instantaneous dipole, induced dipole, the really annoying one that takes ages to write the name out. So there you go. So if you're asked to list all the types of intermolecular bonding, always say instantaneous dipole, induced dipole. Then if it has partial charges, is a polar molecule, then say permanent dipole, and then if it can do hydrogen bonding, that as well, right? Next question. Given a molecule, you're just asked to explain how intermolecular bonds form between molecules of this sort. So this molecule heptane, how do you get intermolecular bonds between heptane molecules? Pause the video, have a go. And you should make the point that this is instantaneous dipole, induced dipole. I'm going to get bored of writing it, so I'm going to put IDID, and obviously remember that you're not allowed to use that as an unexplained abbreviation in the exam. So then how does that occur? You need to tell that little story of IDID. So talk about random movement of electrons in the molecule. So that's in the molecule, not between the molecules. That gives uneven distribution of charge. And that's known as an instantaneous dipole. And then you say that causes an induced dipole on a nearby molecule. And the opposite charges on the two molecules attract. So that's that. So it's a standard explanation for instantaneous dipole, induced dipole, intermolecular bonding. That can happen between any molecules, but certainly if you've got a non-polar molecule like this, then that's the only type. So make sure you've got that little description there, that little story down to be something comfortable that you can talk about. Okay, You often get questions asking you to predict and explain which molecule has the higher boiling point out of a couple. So you might get something like this, and then something like this. So two molecules, A and B, and predict and explain which has the higher boiling point. So pause the video and have a go at answering that. Okay, so your answer should be that it's B. When you get a question like this, make sure that you state the types of intermolecular bonding present, or the strongest types. So for A, the strongest intermolecular bonds are ID-ID. That's because, being hydrocarbon, there are no partial charges on it, so it's non-polar molecule, whereas B, the strongest intermolecular bonding, is permanent dipole. Again, I'm just going to be abbreviating, but for the exams, make sure you write things out fully. No, you don't have to explain why. If the question just says predict and explain which has the higher boiling point, then the diving in point is the intermolecular bonds present. It would be a separate question to say explain the type of intermolecular bonding found in this molecule. So the explanation, the key thing with the explanation then is that PD-PD are stronger than ID-ID. So it takes more energy to break the intermolecular bonds between molecules of B than A. So this is a very standard answer to a question. So just note the structure. Be very clear, be specific. What is the strongest type of intermolecular bonding present in each one, and any little factors that might affect that. In this case, it's quite simple. One has instantaneous dipole-induced dipole only. The other one has permanent dipole as well. And then compare the strength of the types of intermolecular bond, and then relate that to the amount of energy needed to break them. Okay, next question. If you get shown, what should we have? This molecule. And you get asked to draw a diagram to show the strongest type of intermolecular bond between two of these molecules. So the different types of intermolecular bonding involve different diagrams. Have a think. What is the strongest type of intermolecular bonding between two molecules like that? And how would you draw that diagram? Pause the video, have a go. And hopefully you spotted here that we're talking hydrogen bonding. We've got the delta minus N with the delta plus H's attached. So this fits the requirements for hydrogen bonding. You've got a molecule with delta plus H attached to N, the delta minus NO or F, N in this case, and that can hydrogen bond to a lone pair on the delta minus N on a second molecule, nitrogen, group 15 in the periodic table, 5 electrons in the outer shell. 3 of them are taken up with the bonding, so leaves a lone pair. The diagram then for hydrogen bonding, and they do like to get you to do the hydrogen bonding one because it is the one with the most detail to it. If you draw one molecule, the put on a partial charge, a partial positive on hydrogen, on the hydrogen attached to the nitrogen, one of those hydrogens. And then the bit that is most common for people to get wrong, we need this 180-degree bond angle. So I'm going to highlight it from the bond to the H on into the hydrogen bond. So you need to be very clear that that is linear. So the hydrogen bond is linear with the covalent bond attaching the nitrogen to the molecule. At the other end of that, you get the lone pair of electrons. Make sure they're drawn nice and big and visible. And then that's on the nitrogen on the second molecule. Beyond that, we need to make sure that we have the charges, at least one, the delta minus on the N, and at least one sort of balancing charge, a delta plus H. The rest of the molecule, it really doesn't matter how that's fitted in. But make sure you've got the delta plus H at one end of the hydrogen bond and the delta minus N at the other end, that there's the other partial charge in each of the molecules, so they should always come in pairs. And then you've got the linear structure with the covalent bond on one side of the H and the hydrogen bond on the other side of it, 180 degrees to each other, and the lone pair facing into the right straight into the hydrogen bond at the delta minus N end. Okay, next question. I'm just going to give you a bunch of pairs of molecules, and in each case, you need to suggest which one would have the higher boiling point. So the symbol for boiling point, TB. So if I kind of have an A column and a B column, I'm just going to give you a bunch of things, and you can have a think for each one. Oops, let's see, for the first pair, like that. So which one has the higher boiling point? Make sure you would have a way of explaining your answer. And you should have said A, and that's because with the two polar bonds, you've got twice as many opportunities for permanent dipole intermolecular bonds to form between those molecules. Next pair. Have a think. And for this one, you should again have said A. The explanation being that with the longer chain, there's more opportunity for the instantaneous induced dipole intermolecular bonds to form between the molecules. Always specify the type of intermolecular bonding. It fits into the general category for chemistry questions. If you can be specific, do be specific. Why not show something directly relevant that you know? If you miss it out, you can't get a mark for it. If you include it, you might well. Do be, always state the sort of type of intermolecular bonding that's of relevance. How about if we have Cl2 and Br2? Pause the video, have a think. Which one and why? And for this one, you should be saying B. And this is the most obscure one, I guess. This is about atom size and the number of electrons present. So the answer would be that with B, bromine has bigger atoms, more electrons. So when those move around randomly, this is the story of instantaneous induced dipole intermolecular bonding. When they move around randomly, you'll get bigger uneven charge distributions, so a larger instantaneous dipole. That will then induce a larger induced dipole on a neighboring molecule, and so you'll have a stronger electrostatic attraction between them. So bigger atoms mean more electrons, mean a bigger instantaneous dipole induced dipole intermolecular bonding effect. Okay, the next one. Slight curiosity, this one. Pause, have a good think, see what you can come up with. Is something very specific that you need to think about here, that you might not instantly remember to think about it. So just, yeah, have a think. Okay, so you should have said A. And if you're thinking, well, how would I know? They're both polar. They're both got partial charges on. So we mark those on. We got delta plus H, delta minus Cl. We got delta minus oxygens, delta plus carbon, delta minus oxygen. It's tempting probably to say B on the basis that it's got more partial charges, and so therefore you would think that you could get more permanent dipole intermolecular bonding between them. But the thing you've always got to pause and consider, if this partial charge is in a molecule, is it overall a polar molecule? And so you should spot that this one is actually non-polar. And the shape of carbon dioxide is linear like that. And do you remember that this is the thing where the center of delta minus would be on the carbon like that. So the centers of charge are superimposed. So they cancel. So it's not a polar molecule. For this one, for the other one, we've got the center of delta plus on the hydrogen and the center of delta minus on the chlorine. So the charge centers are not superimposed. So they don't cancel. So it is a polar molecule. Okay, so look out for that. It's just a common little trap to fall into. Always, if there's partial charges, just stop and think. Is this one of the weird ones where the symmetry of the molecule, the shape and the symmetry means that the charges cancel out, and even though there's partial charges on individual atoms, it's a non-polar molecule overall. If it's a non-polar molecule overall, then you're talking instantaneous dipole, induced dipole, intermolecular bonding. Okay, one final one. How about if you have this molecule and this molecule? Pause the video, have a think. And here the answer would be B. So this is the higher boiling point. And this falls into the same category that got a brief mention when we were introducing intermolecular bonding of sort of branching and the shape of molecules. It's more linear. So they will pack more closely. So more opportunity for ID intermolecular bonds to form. For A, it's more of a kind of spherical shape, more of a ball shape, and so this you just can't get as much contact between two of the molecules. They kind of meet at one point, but they can't sort of stack up, lining up with each other. So that packing idea. So key message is with boiling point or melting point predictions, you're always trying to think which one has the stronger intermolecular bond, and then you can relate that to the amount of energy needed to break the intermolecular bond. However, there's quite a lot of factors to think about. There is what type of intermolecular bonding. So instantaneous ID compared to PD compared to hydrogen bonding, how much of it there is. So for very long chain molecules, lots of opportunity for ID to form. Also, the things like the packing sort of branched or more spherical shaped molecules compared to more linear molecules, and subtle things like, is the molecule polar or not, based on its shape and symmetry, and also how many electrons are present in the atoms. Are there any big atoms with lots of electrons? Okay, that'll do for this little section.